Hello guys, today we're talking inequalities by induction. Let's go. Okay, man, so we already know how to solve equalities using induction. However, how to emulate that knowledge to inequalities? Well, you know that when trying to prove an equality using induction, we first of all have to try some kind of a base case. If it's true, then lovely, we can assume that the statement will hold for some particular number in the domain of the statement. Awesome, now we can go on and prove the statement for the consecutive one, I mean the number in the domain of the statement that is just after the one we assume the statement for. However, how do we emulate it to the inequalities? Well, the nice thing is that it's actually easy, it's pretty simple, it's pretty similar in both cases. And so I would like to show it to you guys on an example. We're supposed to prove that for all natural n's, so the constraint about the variable being from a set with a well-defined succession, which, by the way, if you don't know why this constraint is really important, I highly encourage you to check out my previous video on induction where I cover it. But this constraint is met in this case, and n is greater than or equal to 4. Lovely. So you're supposed to prove that 2 to the power of n is greater than or equal to n squared. Lovely. So first of all, let's try and solve the base case. I mean, the base case scenario, the base case here is going to be the case of n equal to 4, as well. This is the smallest allowed n of our problem. And so for n equal to 4, what we're going to get is, well, just 2 to the power of 4 greater than or equal to 4 squared, supposedly. However, well, calculating this is 16, this is 16 as well. Well, those two are equal, which is absolutely lovely, because then the greater than or equal to how to say it, relation holds perfectly, which is exactly what we wanted. Lovely. Now we can go on and assume that there will exist some kind of a variable in the domain of this statement, which I will once again say, because I have no idea what that word was, so once again say that it's natural numbers. We're gonna assume that there exists some kind of a natural number k, and that k is greater than 4, such that 2 to the power of k is greater than or equal to k squared. Lovely. Well, this k is kind of too little. Now it's better. Lovely. But what we're supposed to do now? Well, now the fun begins. We're supposed to do the induction step. We're supposed to prove this inequality, which is 2 to the power of k plus 1 is greater than or equal k plus a1 squared, not to the power of alpha, but squared. Lovely. Better. So, how do we do this? Well, it's kind of tricky at first, but let's try and work out through this together. So, what can we do with k plus 1 squared? Well, I'm thinking maybe we could expand it. Why would it be nice? Because then we would get this, k squared term, and we have some assumptions about k squared, so, well, it seems reasonable to go on and multiply this whole expression out. So we're gonna get k squared. This k is once again a little bit too small. So k squared plus 2 to the power of, not to the power, but 2 times k, and then plus a 1. Yeah, lovely. But now there's one thing. K squared, we assumed, is always less than or equal to 2 to the power of k. Yeah? Awesome, do you see it? Now, we could actually do a kind of a chain inequality here, because we know that 2 to the k is greater than or equal to k squared. And so we also know, not an alpha, but 2 to the power of k plus 2 times k and plus a 1 is going to be greater than or equal to k squared plus 2 times k and plus a 1. Yeah? Well, that's nice. That's really nice. But now, what do we really want to achieve here? Because it doesn't really prove anything. Well, look at this. If we manage to prove this one more inequality, so that 2 to the power of k plus 1 is greater or equal to 2 to the k plus 2k plus 1, which is greater than k squared plus 2k plus 1, which is k plus 1 squared, I mean expression squared. Well, if we manage to prove this inequality, then the whole problem would be solved. And so, well, let's try and do it. Let's give it a shot. I have no idea if it's gonna work. I mean, okay, I have an idea. I know it's gonna work, but you don't have an idea if it's gonna work. Lovely. So, we would like to prove that 2 to the power of k plus 1 is greater than or equal to 2 to the power of k plus 2 times k and plus a 1. Yeah, lovely. So, what I would like to do here, is bring this 2 to the power of k to the left-hand side of the equation. This is my left-hand side, this is my right-hand side. I'm mirroring this video if you didn't notice. And what I'm gonna get? Well, I'm gonna get 2 to the power of k, and I factor everything out. Here I'm gonna get 2 to the power of 1, which is just 2, and then minus a 2 to the power of 0, which is just 1, and so this is gonna give me a 1. Nothing changes on the nothing changes here. And on the right hand side I'm gonna get 2k and plus this beautiful 1, which is kind of too small. Yeah, better. So, right now. Well, this one is just as hard to prove. So, is it kind of like, you know, how do you say it in English? You know, some kind of an alley where there is absolutely no way out. No, this is not such an alley. We can actually use our assumption once again. And how can we do this? Well, we know that 2 to the power of k is greater than or equal to k squared. And well, then if k squared would be, hopefully, please, greater than or equal to 2k plus 1, well then 2 to the power of k would be also greater than or equal to 2 to the 2k plus 1. I mix up exponents and multiplication, which is kind of funny. Anyway, well, then I would like to construct one more chain inequality here. So 2 to the power of k is greater than or equal to k squared. It is greater than or equal to 2k plus a1. And I would like now to focus on this inequality. And how are we supposed to prove it? Well, I would like to bring this 2k and this plus 1 to the left-hand side of the equation. Be proud of me, I didn't say 2 to the power of k, but 2k, finally. Yeah, lovely. So we're gonna get k squared minus 2 times k, 2 times in a row. And minus a 1, and then it's greater than or equal to 0. Supposedly, we are trying to prove it, yeah? And so, that would be actually nice to add 2 to both sides of the equation. And why would be nice? Because then the left-hand side would be something like this. It's gonna be k squared minus 2k and then plus a 1, and the right-hand side is gonna become just a 2. But now the left-hand side is just k minus a 1 squared. Yeah? But you know what's nice? K is always greater than 4. And if k is greater than 4, maybe I will even write it down. If k is greater than that, not like 0. If k is greater than 4, then k minus 1 squared is greater than 9. And 9 is absolutely greater than or equal to 2, which I've once again wrote absolutely terribly. Yeah? And so, well, it's absolutely lovely because this separation here proved this inequality. And why did we want to prove this inequality right here? Because this inequality implies this inequality, which, well, is the statement we were trying to prove. So, we created a chain 2 times. Two times we created a chain of inequalities, and so we will prove the statement. I have no idea how to say it more explicitly, guys. So, that's the end of the problem. Okay guys, so the second problem, we're supposed to prove that for all natural numbers n, why am I putting there? I have no idea. For all natural numbers n greater than or equal to 4, n factorial is greater than or equal to 2 raised to the power of n. Lovely. So we're gonna use induction to do it. Why are we gonna use induction? Because n is in a set that has a well-defined successor, which means that we absolutely can do it. Lovely. So first of all, we have to achieve the base case here. So the base case scenario is gonna be n equal to 4, as is the least value in the domain of the statement. For n equal to 4, we're gonna get that n factorial, which is 4 factorial, is greater than or equal to 2 to the power of 4. 4 factorial is 2 times 3 times 4, which is equal to 24, and it's supposed to be greater than or equal than 16, which is indeed true. Let me change the marker because this one's kind of dying. And this one's dying too. It's dying somewhere, Mexico, close to American border. That's sad. Okay, lovely. So I have a new fresh marker. Now we're ready to make a nice assumption. We'd like to assume that there exists a particular number k. Assume that there will exist a natural number k in k. Yeah, I'm good, man. Yeah, and that k is greater than 4, such that k factorial is going to be greater than or equal to the power of k. Lovely. So now we would like to do the induction step, which means proving that k plus 1 factorial is greater than or equal to 2 to the power of k plus 1. And I would like to do it, well, in a way that is not quite algebraic, because, well, people usually... the beautiful thing about induction in Mathematical Olympiads is that you almost always, in those harder problems, use it not in this algebraic way, in, well, you know, like algebraic, you manipulate some kind of expressions. You use it as some kind of an argument where you use words instead of mathematical symbols and expressions to say what you would like to, what your assumption implies in terms of the statement for the consecutive number. And so what I would like to observe here is when we went from k factorial to k plus 1 factorial, what we did is we multiplied the left hand side by k plus 1, because, well, k plus 1 factorial is just k factorial times k plus 1. Yeah. However, what we did in order to get from 2 to the power of k to 2 to the power of k plus 1 is we multiplied 2 to the power of k by that factor of 2. And so notice, k factorial by our assumption is greater than or equal to 2 to the power of k. But as k is always greater than 4, and so k plus 1 is always greater than 5, absolutely k plus 1 will be greater than 2. And so initially k factorial was bigger than 2 to the k. Yeah, you probably can see it because of my left hand. Yeah, lovely. And now we multiplied the number that was bigger initially by the number that is bigger than the number that we multiplied, the number that was smaller initially. I have no idea if you get me. Yeah, so k factorial was initially smaller. We multiplied by a number was bigger. 2 to the k was initially smaller, and we multiplied by a number that is smaller than the number we multiplied k factorial by. And so absolutely k plus 1 factorial has to be greater than or equal to 2 to the power of k plus 1. Normally I would have to, write it all down but first of all, there are two arguments opposing that idea of mine. First of all is well, that I'm my mark is kind of dying, and the second one is, well, my absolutely terrible handwriting that would probably kill all of you and the half of the human race. So we're gonna skip that. We're gonna just put the beautiful, almost filled in box, and I will leave it as an exercise to the reader to script the beautiful comment to that solution oneself. Okay guys, so we can move on to the next problem of today's video. We're supposed to prove that 1 plus a half plus the quarter, and we're summing stuff up to the reciprocate of the nth power of 2 is always less than 2, is strictly less than 2, for all n's that are greater than or equal to 0. Lovely, let's try and do it by induction. So we know that we also know that n's are natural, just by the way. So for the base case, we're gonna have n equal to 1, which is just the smallest possible n from the domain of the statement, and so we will get that 1 plus 1 and a half is supposed to be less than 2, well, which is true because those are just 2/3, and this is something like 1.5. Lovely. So right now it would be nice to make some kind of an assumption, and I would like to do some kind of an assumption here. Assumption, you're right, it's not the easiest part. Assumption that there exists a k such that k is natural, and that k is also greater than 1, such that 1 plus a half, and then we are summing stuff up to the the reciprocal of the cave power. Cave power. There were cavemans, and cavemans had cave powers of numbers anyway. The cave power of 2, and it's supposed to be less than or equal to this weirdly looking alpha, which is supposed to be a2. Lovely. So right now I would like to use this assumption. Let's try and see how this segment would look like for k plus 1. And for k plus 1, it would look something like this. We would have just a 1, then, I don't know what, maybe I will make it a little bit bigger. So we will have a 1, then we will have 1 over a 2, and then we are adding stuff up to 1 over 2 to the power of k, and then we have the last term of this sum, which is just 1 over 2 to the power of k plus 1 is supposed to be less than 2. Yeah. We are kind of stuck here, guys. Kind of really. You see why? Well, this sequence right here is increasing. Kind of really increasing, yeah. I mean, with every single next k, its value is getting bigger, yeah? I mean, the sum from the 0th up to k plus 1th power is greater than the sum from 0th to the kth power, yeah, and so on. And so, even though this sum was less than 2, it doesn't really mean that this sum was less than 2, yeah? So, is this statement false? Or maybe this statement is just maybe this statement is just too difficult to be proven by induction. No. And this, ladies and gentlemen, is so-called paradox of induction. You know, let's consider this statement. One more statement. Yeah, I will even write it down. It's supposed to be T. Statement. Lovely statement. Statement such that this 1 plus a half, and we are adding stuff up to the 1 over the nth root of nth power of 2 is going to be equal to 1 over 2 to the power of n. Oh, sorry. It's going to be equal to 2 minus 1 over 2 to the power of n. Well, let's assume that it's true for n. I mean, you see, it's true for n equal to 1. It's gonna be 1 plus a half, and here we're gonna get 2 minus a half. Well, those two are both three halves. Well, let's assume it's true for n, and I will even write it down, okay? Assume for n. I'm gonna assume it for k, just for, you know, like, just for the sake of time. Okay, so for n plus 1, what we're gonna get? Well, 1 plus 1 over 2, and we're adding stuff up to the nth power of 2, and then we are adding that n plus 1th term of that sequence, yeah? And it's supposed to be equal to 2 minus 1 over 2 to the n plus 1th power, yeah? But now this stuff right here is literally just 2 minus 1 over 2 to the nth power, isn't it? And so we can rewrite this whole bunch of things. You know what, I'm gonna set a clear boundary here. I'm gonna move here. Yes, we can write it as 2 minus 1 over 2 to the power of n plus 1 over 2 to the power of n plus 1 is supposedly equal, and my marker is dying. Can you see it properly even? Yeah, barely. Lovely. Bear with me then. 2 minus 1 over 2 to the n plus 1th power. But notice that this stuff right here, I mean this fraction, is just 2 times 1 over 2 to the n plus 1th power. And so what we're gonna get here is actually, well, this side, the left hand side of the upper hand side is gonna become 2 minus just 1 to the n plus 1. And well, this is indeed equal to 2 minus 1 over 2 to the power of n plus 1. So what's going on? I mean, this is clearly less than or equal to 2. And so this statement actually is true. I mean, this statement is actually true for every single value of n. So why couldn't we prove by induction? Well, this is the paradox of induction. Sometimes there are statements that are just too weak to be proven by induction, and we have to strengthen them. And what does it mean for a statement to be strengthened? Well, to be strengthened, to be made more strong. Yeah. Well, this means exactly what I did right here. I made it more rigorous. Yeah. I mean, in a way, even intuitively, it is more rigorous. I threw in some more constraints about the problem. Or you can simply just understand it as rephrasing the problem in such a way that it's achievable by induction. So, well, that was funny. You know what? Let me show you a couple more examples of how to strengthen a statement, so you can grasp this concept a little bit better. Okay guys, so lovely. We would like to prove that the product of, well, those with fractions where in the nominators we have odd numbers and in the denominators we have consecutive even numbers up to 2 times some kind of an n minus a 1 all over 2 times an n, and the same n is less than 1 over the square root of triple that n. Someone popped a champagne bottle just outside of my window. That was a nice sound. Anyway, and it's for n greater than or equal to 1. Lovely. So, we would like to do it by induction. So first of all, we have to check the base case and how it's going to behave, how the system is going to behave for the base case. So the base case scenario is n equal to 1 here, as n is the least value in this domain of this statement. So, for n equal to 1, we're going to be multiplying stuff up to 2 times n minus 1 all over 2 times n. So it's going to be just 2 times 1 minus 1, which is 1, over 2 times 1, which is 2. So we will multiply everything up to 1 over 2, which is, well, the first time on the sequence. So lovely, we're not writing anything more, and it's supposed to be less than 1 over the square root of 3 times n, which is, well, just 3 times 1, which is 3. So as 2 is greater than square root of 3, because 2 is approximately 2.0 and square root of 3 is approximately 1.7, this inequality will hold. Lovely, we have the base case achieved, and now I would like to make an assumption. I would like to make an assumption that the strategy I have absolutely no intention of rewriting once again, and so I will just call it P of n, that P of n holds, you know what, for variety I will not call this constant k this time, I will call it n, because I'm too lazy to rewrite everything in terms of k. P of n holds for n. What about n plus 1 then? Well, we would like to prove that n implies n plus 1. Quite lovely. And so I would like to use the same trick that I used approximately 2 problems ago, I guess, about, you know, comparing the things we multiplied both hands sides by in order to get from the state of the assumption to the induction step. And so let's recall what this step, how this step looked like when we were at the, you know, assumption step. It was P of n is less than 1 over the square root of 3n, yeah? Awesome. And now what it looks like after subbing in n plus 1 for n, well, it looks like this. P of n times 2 times n plus a1 over 2 times n plus a2. Why is it so? Well, we're just adding one more term to this sequence on the left hand side right here, and the, you know, consecutive term is gonna be 2 times n plus 1, yeah, the next odd number, divided by the next even number, which is just 2n plus 2. Awesome. And, well, what about the right hand side? I mean, it doesn't quite change in, like, you know, the product kind of way. We're literally just adding a 3 under the square root. I mean, we're adding... but yeah, we can actually make something up, yeah? So we know that after that multiplication, we will have to get something like 1 over the square root of 3 times n plus 3. Why plus 3, not plus 1? Well, because we will multiply n plus 1, you know, expression by 3, not just the n. Quite lovely. So I would like to actually say that we will have 1 over square root of 3n, and then we will multiply this by this beautiful fraction such that so that those two will cancel each other out. We will be left with just 1 over the square root of 3 times n plus 3. Awesome. But now, you know, notice our assumption was that, well, Pn holds for n, and so that P of n is less than 1 over square root of 3 times n. And so we know that P of n is less than this, yeah? So that actually be sufficient to show that 2 times n plus 1 all over, well, alpha, or 2, if you will, and 2 times n plus 2 is less than or equal. It can be also equal. I mean, if this one was less than this one, then if we multiplied both of them by an equal number, this hand side would still be less than this hand side. And that is less than or equal to 3 times n square root of 3 times n all over the square root of 3 times n plus a 3. Lovely. You know what? Let's try and prove it. So we will get that 2n plus a 1 over 2n plus a 2 expression squared is greater than or equal. Well, I will even divide out those 3, so we will just have n over n plus 1, and guess what? Is it true? I am not going to be multiplying this whole stuff out because I'm just too lazy for that. However, you might check that is absolutely not true, yeah? And so, what are we supposed to do here? We're out at a destination where we can't really seem to have any way out of this place. Is it wrong? Is it wrong? Or maybe we made some kind of mistake? No, we didn't. This thing is just too weak to be proven by induction, and we have to, guess what, strengthen it. And so how are we going to do this? Well, notice the part where we actually started to have trouble with this problem, yeah? It was here, multiplying this stuff out. I'm thinking, what if we could add some kind of a variable, some kind of a constant, yeah, here, and for example, an a under the square root, and this one. Okay, guys, so I got kind of caught there. My camera died. Anyway, doesn't matter. We're going to get through this together with the power of love. So let's just get back to the problem. So where we were at? Lovely. So I came up with an idea of just taking some kind of a constant, like an a, for example, and adding it to this 3 times n under the square root, and to this 3n plus 3 also under the square root. Why can I do it? Well, I mean, I'm kind of changing my statement here, yeah, because I'm adding something under the square root. However, the nice thing is that I absolutely can do it. Well, I'm strengthening my statement in a way that I'm saying that p of n is going to be less than something, 1 divided by the square root of 3 times n plus some kind of a constant a, but this is actually less than 1 over the square root of 3 times n. And so I'm actually making my statement even sharper. Absolutely lovely. So let's try and do it. Let's try and figure out the value of a that will satisfy this this statement if one exists. Lovely. So let's try and do it. We want maybe I actually get rid of a bit of this stuff here. Lovely. So I will say something like this. We would like to find an n such that 2 times n plus a1 all over 2 times n plus a2 squared is less than 3n plus that a all over 3n plus 3 plus a. Beautifully. And so what we can do here? Well, we can absolutely just multiply everything out, which is gonna be absolutely awful, but let's do it. Who cares, actually? We will get something like this. We will get 4n squared plus 4n plus a 1 all over. Oh, let me pump my marker real quick. It's kind of dying once again. Yeah, lovely. Should be better. Sticker is useless. Lovely. Here I will get not 2 but once again 4 squared ends. I will get 8 times n, and I will get a 4 here, and I will say, oh yeah, that is actually less than or equal to 3n plus a all over 3n plus 3 plus a. Yeah, I should have put less than or equal to sign here. Anyway, well, yeah, now we kind of have to multiply everything out, cross-factoring stuff. Yeah, hate it even more. Hate it even more. Lovely. And so 12n cubed I will get. 12 of regular n's I will get. 3 additional n's I will get. 12n squareds I will get. Plus, and then 12 additional regular n's I will get. Then I will get a 3. Then I will get, and I will actually not multiply this out, I will just leave it in front of the parentheses. Well, this was supposed to be 2, not an alpha. I'm kind of struggling writing a 2 on this board, as you can see, but I'm gonna get used to it. Yeah? 4n squared plus 4n plus a 1, and it's supposed to be less than or equal to, and I will actually write it in the next line. And I will get 12n squares, I will get 24 regular n's, I will get also 12 n squares. Yeah, did a mistake here. I should have put a square here as well. Nobody cares actually, yeah? Lovely. So 12n, and then plus, and once again a, I will just leave it here, 8n plus 4. Beautifully. So this stuff, oh yeah, it should be in the third power. Nobody cares. It's gonna be, this is gonna cancel out. Here I have 12 and 12 and squares, so this is gonna cancel out with 24. Here I have this 3, here I will just get 9. And basically after all of those manipulations you will get that a equal to 1 satisfies. There's absolutely no intention of simplifying this because it's an absolutely awful thing and I've been recording for hours and my brain is dead. So I will just erase it. We've come to the conclusion that a equal to 1 satisfies. Yeah, lovely. And so what can we do now after clearing the board? Let me elaborate on it real quick. So we wanted to prove that p of n times the 2n plus a 1 over 2n plus a 2 is less than, well, I will just say 1 over the square root of 3n plus 3. What we did instead is we proved that Pn, well, we actually strengthened the statement, yeah, and so our assumption kind of changed for something like this, that p of n is less than 1 over the square root of 3n plus 1, and so our proof section right here also changed into p of n plus 1. I'm going to be rewriting this multiplied stuff once again, is less than 1 over the square root of 3n plus 3 plus 1, which is just plus 4, and this is actually less than 1 over the square root of 3n plus 3, which is actually exactly what we wanted to achieve, and thus solve the problem. We solved the problem. Never mind. Okay guys, so the last part of today's video is as follows. It's supposed to prove for all n's that are greater than or equal to 2, this beautiful sum of 1's divided by consecutive squares of numbers from 2 up to n is always less than 1. And so you see guys, we are screwed, like 100% screwed in this problem. Why is that so? Because this sequence is strictly increasing. With every single, with n increasing, this sequence is increasing as well. And so even if we assume that for some n, this sequence is, this sum is actually less than 1, if we then evaluate this sum for n plus 1, we will get this additional 1 over n plus 1 expression squared factor here, which unfortunately might make this whole sum get bigger than 1 in the end, which we absolutely don't like. And so, you see, I would like to show you guys a nice trick here that I like use very much. Well, first of all, one caveat here. Absolutely, if you know, for example, D'Alembert's criteria for convergence of sequences and you know a little bit of calculus and stuff, it will be much more easy for you to do so. However, I would like to present the induction approach in this video. So, we will create ourselves a new sequence. Yeah? First of all, I will denote this sequence right here as x of n, x sub n actually, and I will create myself a new sequence which I will call y sub n. And I will say that y sub n is equal to x sub n plus some kind of a function f of n. And I will say that f takes only, it gives only positive values, yeah? So it gives only plus, so positive values, yeah? And one more constraint, that yn is non-increasing, so that nth term of yn will be greater than or equal, the worst case scenario, equal to yn plus 1. Yeah, so I will say that I will create yeah, y of n. So y of n is by the definition x sub n plus f of n, and yn is going to be equal to yn plus 1. Lovely. And so what actually will give me? Well, if I manage to find the function f of n such that I will be able to find such a sequence y sub n, well, why is it awesome? Well, notice that yn is actually a decreasing sequence, so I will not have this problem of the sequence being increasing when trying to prove that it's less than 1 by induction. Yeah? So I will be able to prove that yn is actually less than 1. The nice thing is that since yn is equal to xn plus some function f of n, but this function gives only positive values, y of n is greater than xn. And so what does it imply? Well, it implies that 1 is greater than xn, and so this is exactly what we want to prove in the original statement. Yeah, lovely. So let's try and do it. Let's try and figure out what this function f of n might be. Lovely. So you see, from combining those two expressions, we can actually deduce the yn, which is equal to x sub n plus f of n, is greater than or equal to the x sub n plus 1 plus f of n plus 1. Yeah? Beautiful. So now, actually, I can subtract f of n plus 1 from both sides of the equation and subtract x sub n from both sides of the equation, and what will it give me? Well, on the left hand side I will be left with f of n minus f of n plus 1, and on the right hand side I will be left with xn plus 1 minus xn. However, now notice, what is xn plus 1 minus xn? Well, actually it's gonna be just the n plus 1 n plus first term of the sequence x. Yeah? Why is it so? Well, here you have xn, yeah? And if we were to write down xn plus 1, well, it would be just 2 squared, yeah, stuff, up to 1 over n squared, and then 1 over n plus 1 squared. This is the n plus 1 term, yeah? And so, if we take this sum right here, and we subtract this stuff from here, what we will get, well, this stuff will cancel, yeah? There will be no of it, yeah? We will just have this right here, and so this is equal to 1 over n plus 1 squared. Beautiful. But what really gives us? I mean, we have those f of n's. How do we figure that? And we figured out by absolutely beautiful strategy, which is absolutely random, stupid guess. I love it. Yeah. So, what function do you think will decrease at a rate similar to 1 over n plus 1 squared? Well, I think that function of n is something like maybe k over n squared might be a nice option. No idea. I mean, let's try and do it, and maybe let's figure this constant k out. It would be actually pretty nice. Yeah. So let's plug it into the into our inequality here. We will get that k of n squared, k over n squared minus a k is supposed to be a k, not a mu, k over n plus 1 squared is going to be greater than or equal to 1 over n plus 1 squared. Yeah, and now notice one thing. Actually, the nice thing about it is that this is supposed to be holding for all values of n that are in the domain. Yeah, so what is the least value we could just substitute in here, just so we don't have to care about all those awful n's right here? Well, the smallest n in the domain is just 2, so let's plug it in and let's try what we're gonna get. We're gonna get k over 4, and you're gonna get k over 9 is greater than or equal to 1 over 9, which is absolutely lovely, because now it's supposed to be a 9, yeah? And so now we will get that 9 times k over 4 minus a k, which is just 4 fourths k, is greater than or equal to 1, and so we will get that 5 over 4k is greater than or equal to 1, and so it will yield that k is greater than or equal to 4 over 5, which is awesome, because, well, now we can just say that our function f of n will be equal to, well, k is 4 over 5, so 4 over 5 times n squared will be the function. And so, well, we managed to find a function like this, actually. It's nice. Now let's check if it will actually hold, yeah? So let's now we want to prove, maybe I will even write it down, we want to prove that y of n is less than 1 for n greater than or equal to 2. And so we do it by induction. First of all, we have to consider the base case, and the base case is going to be just n equal to 2, as is a, I'm not going to be saying this, oh, maybe I will say it, n equal to 2 is the smallest value in the domain of the statement. Anyway, y of n is just xn plus fn. xn for n equal to 2 is 1 over 4. 1 over 4, what about f of n for n equal to 2? Well, it's going to be 1 over 5. Well, this is certainly less than 1. Lovely, it works. I mean, the base case works. Now we can just assume for n, because, well, k is already taken, I'm not creative today, yeah? We will assume for n that y of n is less than 1. And so, well, for the induction step, we want to prove that y of n plus 1 is less than 1, but y of n plus 1 is literally less than or equal to yn. And so we will get 1 is bigger than yn, which is bigger than or equal to yn plus 1, which completes the induction and, well, solves a problem. Okay guys, so that will be all for today. Make sure to deeply internalize everything we've covered. I hope you like this video, and, you know, see you in the next one.